So can you see the screen now?
Yes, sir.
Yes, sir. Okay. So in the last class that we discussed about how to compute regression analysis, and this class we will learn some more features of regression analysis, because this is a kind of a very modeling type, prediction type, and there are many criteria which are associated with regression analysis. And before starting, let me tell you what we are discussing today is the actually in our syllabus we are discussing linear regression or bivariate regression, which is linear. There are also multiple regression analysis you can have. So here we are mainly concerned with bivariate. Only one option is there that I will discuss on multivariate, right? So there, here you can see this. We have discussed that whenever we go for regression analysis, we generally what we do first we need to check the scatter plot diagram, whether the scatter plot is fine or not. See, this is scatter plot, negative correlation. This is more or less positive correlation, right? But not very strongly correlated. But even though you can see the pattern of the whole thing is positive or negative. So whenever you go for regression analysis, just check whether it is a very finely distributed positive or negative, right? So this is first condition, and here you can see the in a data, as you know, the main emphasis is given on the regression line. This is regression line, right? It may have a slope, as I told you, or it may be very slope is very low. So whatever is that, whatever data you get, the all emphasis is given on the regression line. And if all the coordinates are falling on the line, that is good relationship and good regression. Prediction is very good. But if they are not falling on the line, the prediction is not you can say it may have some kind of variations. Right? This is second point. And here, as we discussed last class, that R, or as someone told, is R square. Yes, it was R square. I'm correcting that question. So what is R? It may be written as R square, R capital R also, right? Small r, capital R, no problem. So here you can see these three diagrams. This is 9.0, oh sorry, 0.90, 0.50, 0.10. Now what happens? The pattern, you can see the R square. Looking at the R square, you can see the pattern. 0.5, you can see the pattern, and 0.10, you can see the pattern. So this pattern itself is self-explanatory, which you can say the what would be the look, or what could be the slope of the regression line, that you can assume, or you can think of from the looking at the R square. So this is one thing that we need to know, what is the importance of R square, right? So this is again you can have, that I told you, this R square is very crucial point, coefficient of determination. And best fit line, this is best fit line, this is called best fit line, right? So here you can have that one R. Now even though sometimes what happens, you can have a good best fit. You can see the difference between here, the best fit is a difference. There is difference between this best fit, this best fit and this best fit, right? So these two best fit line, their difference. But in the second case, you can see this case, they are all fitting very well to the regression line, but still the R's are different. What is the reason? Is that in the smaller the size of X, the smaller the value of R square. Means that, see, the number of X means here the values, or Y2, it depends on the X, right? So number of X you consider, you will get equal number of Y. So we need to look at how many X we are taking. So X, number of X, it depends on it will decide if we take if there is a good regression model. If you take a number of x, you'll get a very high R square. And if you even though it's best fit, if you get a smaller number of size of x, you may get this kind of what is called regression line. So there you can say that here your x is deciding the deciding the R square. So we need to be very careful when suppose you are given a problem to deduce the regression coefficient or the regression relationship, but if you take a less number of R, then x, then it will be difficult for you to find the actual R square. So better to take around 10 to 20 x, so that you can have a good regression in your while solving the problem. So here another part that I told you, the residuals, right? What happens generally we go for R square, right? That earlier you can see R square, we are predicting the best of the model depending on the R square. But here you can see this part R square is 8.1. Sorry, R square is 8.1. Then you are getting a good fit. Then R square is 0.24. You are getting a regression line, but not a good fit regression line. So what happens, whether if it is a good fit, then our predicted and actual, that last class I told you that we have to go for back calculation. Means once you get the model, we can recalculate the y from considering x from the beginning. So we can predict the model from the actual value. Are you getting the point? Say for example, you have deduced your model from a data 2, 4, 3, 6, 4, 8, 5, 10 like this. Now from here, x and y, you have that, as I told you, we have calculated a and b, and we'll get a model y equal a plus bx. Model you get bx, and this model you will get a value of b, you will get a value of a. Now when you get a value of b and a, replaced the x by 2, then you find a value of y, which may not be 4, it may be suppose 5. So this is called actual value and this is called predicted value. So when you get a model a and b with the coefficients, you calculate back the y, which is called predicted value of y, and there will be a actual value of y also. So we need to compare both of these. So you can see actual value of y and predicted value of y. You can plot it on a graph. If the model is very good, best fit model, you'll find a very good graph. And if the model is not very good, likewise the 24, as I told you, you may not get this kind of graph. So it is like this, right? So this condition comes, but all the time it is very difficult to find out, this graph, that one graph that you have to draw from like this, plot again and draw the graph. So we have a way to find out, to explain how the actual value and predicted value fits to the model. So you can see this is what we got it in predicted value and actual value of that particular concept from the earlier slide, right? This slide, right? So here from you can easily can understand this predicted and actual value. We can plot it, and this is what, as I told you, predicted value and standardized residuals. As I told you, if the model is very good, the values will move around the line. So it means they will fit on the line. If they perfectly fit on a line, the value will become 0. So 0 is there, 0 is there, this is 0 line, you can see. So it may be more than the actual value or less than the actual value. If it is more than the actual value, you can find it on the positive side. Less than the actual value, you can find on the negative side. So that way you can find a distribution of this whole plots of the y values, right? So this is called residuals, and it is a kind of residual plot. There are different ways of plotting residuals. So this is one way, and this is the best way, and we can easily explain the nature of the model depending on this kind of distributions. So let me check how can it explain. See here, there are three different types I am showing you. This is 1, 2, it's almost same, right? So this is first one, residuals. This is increasing. See, this is increasing, right? And second case, this is decreasing. And third case is there is no increase or decrease. So we can, these two models, number 1 and number 2, these two are known as heteroscedasticity. So remember the name, heteroscedasticity, right? And if it is like this, it is called homoscedasticity. Homoscedasticity is the expected one. Now, when a residual plot is homoscedastic, or you can say homoscedasticity, it is the expected one. Or if it is like that, if it goes like this one, right? Say for example, it goes like this one, first one. The first one, see, the model deviates. Initially, model will be fit, but slowly it is deviating, right? And in case of second one, model at lower values, when the values, x values are very smaller, then it deviates. But when it goes higher side, x values are increasing, the model is fitting. So depending on that, we can easily understand. Yes, maybe the higher the muscle power may be related with the higher age of the person, not in a very early childhood age. You cannot, that kind of prediction can be made. So many conditions are there where these kind of models are fit, and some conditions are there, these kind of models are fit. And here, in most of the common cases, the homoscedasticity models are fit and expected. So this is one, you can say the way you can explain the homoscedastic or heteroscedastic behavior of regression residuals. And there you can see this is homoscedastic, how the graph it shows. It shows a completely kind of a uniformly increasing trend around the regression line. So this behavior is mostly, you can find in a very uniform increment of two variables. So this is one. You can say the two properties you can remember, heteroscedasticity and homoscedasticity, right? And there is another very important part which is associated with regression analysis, and this is called collinearity. Collinearity is a very serious part, right? A very serious part, collinearity, right? Collinearity. Now, suppose you are taking a number of parameters, say for example age or weight, or you can say the fat intake, right? Now you want to determine the disease condition of a person. Now since you know that weight is related to the fat intake, so in that case, if you take weight and fat together, they may not give the exact prediction because they are collinear, they are correlated. So when we want to give a prediction for a particular y, and we're taking some x which are correlated, we need to be very careful because correlated topics, correlated variables, they never give actual prediction, because during correlation they used to lose their predictive ability. Are you getting my point? Suppose when we talk about independent, when you say, what we say, a y equal a plus bx, right? X should be independent. It should not be related to anything else. Now suppose you are taking multiple regression analysis. That is what here we need to very careful regarding multiple regression analysis. So x is related to a kind of another y, another x1, bx plus cx1, right? cx2. So now this x1 and x2, these are correlated. In that case, the y actual prediction may be different. So we need to check whether the independent variable what I have taken is independent in true sense or not. If it is dependent, virtually dependent on some other variables, means they have some correlation, we need to minimize that one, and that minimization can be done by applying a method called variation inflection factor, VIF. VIF is very you can see here, this is how it is calculated. We are not going to calculate R square VIF because these concepts are related with regression. So we should know that when we are actually practicing with regression, we should know what is homoscedasticity, what is heteroscedasticity, what is variation inflection factor, right? So this is R square of Z. Suppose there are two variables you are taking, age and weight. So age and weight are correlated, for example. So we need to compute them. Rj, R square of age and weight, right? Age versus weight, okay. And again, suppose we are taking another factor, fat intake, right? Age versus fat, weight versus fat. So for every correlation, we have to find the R square from here, and then we can compute this one. Okay? So while computing, we'll get some values. The values will be like this. See, you can see the values will be like this, like these values. So against each component, we'll get a value. How they're dependent with another. So in that case, once we get a variation inflation factor, you can determine which one you will be taking, which one will be rejecting. In this case, you can see we will be taking activity, right? This one. So because you can see this here, a value of 1 indicates that there is no correlation between these independent variables and any other. If suppose value comes 1, and if VIS between 1 and 5 suggests that there is a moderate correlation, and if it is above 5, it is not at all considered, and if it goes to 10, the totally rejected. So we need to be very careful while finding out the regression, so that there should not be any variable we should take which are correlated strongly with each other, right? A mild correlation we may accept, because as you can see here, it is 1 to 5. Moderate correlation is it is acceptable, right? So this is how we can address the regression analysis in a very there are many more concepts that are associated, but these two concepts are very important to address regression analysis, right? So this is one regression. Let me go for the